In this case, we're going to conduct a hypothesis test on an educated guess about one of these parameters. It could be the population mean, it could be the population proportion. Collectively, these are nothing but population parameters. One of the examples that we did when we were doing 6.3 is we wanted to find a confidence interval for the proportion of US adults who would keep who make New Year's resolutions. Yes, one of the problems that we did. So we wanted to find an interval. And based on that interval, we were able to make inferences. If you don't recall, what was that problem? The New Year's resolution problem. He was between two values. 29 and 32.
Yeah, I do.
Yeah.
0.03003.
No,
Are you
that
talking
wasn't
the last
new.
one?
No, one before that. What you call
The one that had like 1 million people surveyed?
Not that one.
Oh.
It was 0.271 and 0.3.
Right. So I think we did this before. So based on this, we could say that the proportion of people or US adults who, make New Year's resolutions is somewhere between 27% and 31%. Even if those aren't the numbers, let's just assume that's the case. If that is true, and if I'm the mayor of a city, could I say that in my city, 80% of people make 80% of adults make New Year's resolutions? Would I be correct? Yes or no? No, because it doesn't fall in this interval. If I said only 10% of US adults in my city make New Year's resolutions, would I be correct? No, because I fall on this side. So I don't fall here. If I fall on this side, then whatever statement that I'm making is incorrect. On that side, incorrect. Right in the middle, yes, agreed. So the idea is pretty much taking this concept and putting it in a different way. So not complicated at all. And one may say, well, why should we use a different approach? Oftentimes, we want to put a probabilistic argument in concluding something. Sure, this talks about 95% chance, but in reality, it could be more than that, right? Based on the sample that you see. So instead of simply sticking with a confidence interval all the time, we could come up with a different probabilistic argument. That's where hypothesis testing comes into play. And what are we testing for? We're going to test for a proportion or a mean. Good. So for example, going back to that interval, I can make a claim that P is bigger than 0.4. Good. One claim. Would you say that that is true? No. I could say it's less than 0.1. Would you say that that is true or likely to be true? I hate to use the word true, but we're just starting this out, so I'll keep formal terminology aside. One last thing. Would you say that that is likely? Why? I mean, clearly it is not equal to 0.3. Why would you agree with that? It falls in that interval. I know that this particular interval, based on the data, is reasonable, and this value is likely to fall in the middle. So if I make a claim that P could equal 0.3, then I'm speaking the truth to a certain degree. Do you agree? So in that case, I find some sort of evidence toward the claim that I'm making. So our objective is to follow that logic and come up with a probability value, which is called a p-value, that will put an amount of significance in our conclusion. Does that make sense? If you end up in social sciences or sciences, any sort, when you do an experiment, when you do a study, when you report your findings, p-value is quite important. Of course, people misuse it all the time. That's why you need a statistician to correct you if you're wrong. Are we clear? So that is a basic construct that we use. H sub 0 or H naught, not N-O-T, but N-A-U-G-H-T, like naughty. That's called the null hypothesis. HA, some like to call it H1, is the alternative hypothesis. So alternative hypothesis is simply the opposite of the null. So null, alternative is just the opposite of null. Formally, we denote it as H1, but HA is what your book uses, and sort of is easy to remember. How come? You guys here? Okay. So what does null mean? Null. Incorrect. No, yeah.
That has like no impact, like null and void
No,
impact or like.
no impact. Null means nothing, right? Matt is absolutely correct. He actually is very perfect, was very perfect in defining the null. Null means nothing, no effect whatsoever. So when we define null hypothesis, this is what we mean. Null implies no effect. Alternative implies that there is some sort of true effect. Typically, one would make a claim and we want to verify the claim using the data. And oftentimes the alternative is what we define as the claim. But this or that could be considered as the claim. Commonly, we go with the alternative, but it could be either. equality or the equal sign must be in the null hypothesis. It cannot be in the alternate hypothesis or the alternative hypothesis. Going back to the thing that I just erased. Suppose I claim that P is bigger than 0.4. What should the null be?
Less than
Strictly less than?
or equal to.
Less than or equal to. Correct. If I started with, what was it? Less than 0.1. Earlier, mayor of the city making claims. What should the null be?
Greater than or equal to.
Greater than or equal to. What was the last claim that I made? P equals 0.3. Should I put it in the alternative or the null? The null, because the null must have the equal sign. If P is equal to 0.3, what is the alternative?
It's not equal to.
P not equal to 0.3. Yes, correct.
So you want one, 0.4.
Sorry. Is that your question too, John?
Yeah.
Okay, so. I was looking at the board. So, first case, I had the claim in the alternative. Second case, the start. In the third, I have the claim in the null. So a hypothesis test is about assessing significance. If I want to make a statement, I want to make sure if whatever effect that I observe is significant. So what do I mean by that? Let's take the first case. I have P to be greater than 0.4 as my claim. So suppose the estimate from the data P hat happens to be 0.45. Good. My question to you is the claim true? Which claim? P greater than 0.4.
Yeah.
Are you certain? No. Why not?
I don't know. You just asked me and I got scared.
Okay. Go ahead.
It's 1.4, so the claim would be true, but it's not statistically significant. Like there's not enough of a.
It's not like 0.6 or something. It's just 0.4.
So that's a good example. So 0.4, I have 0.45. Just because algebraically or numerically this number is bigger than that number doesn't mean that the claim is true. Okay? There is a difference between true and significantly true. Yes? different mathematically? Yes. Is it significant? I don't know. Listening. So just because I get 0.45, it doesn't make that claim true. The question to ask rather would be, I should even take that word significant, excuse me, true away. Now I'm getting formal. I should simply say, is the claim significant? All I'm trying to assess here is significance. Is it significant when I look at the hut? Case 2. Suppose the estimate p hat is 0.49. Is the claim true?
Algebraically, the claim in and of itself isn't true, the null hypothesis would be true. It's substantial 1.1, we haven't gotten into calculating statistical significance.
So if I have to conclude, could I say that the claim is false? Absolutely. Here is another question. I don't know if the answer is already. Do I need to assess the significance of my conclusion? No, correct? Because the only time significance matters is when I find evidence toward the alternative. In the sense, if it is bigger than 0.4, is it significantly bigger? Here, I'm saying less than 0.1. If the data gave me a value less than 0.1, then I'd like to know if the data falls below 0.1, is it significantly below, Matthew?
So we don't have to find whether or not it doesn't.
No,
Okay.
it's a trivial case. I will do problems on this, but it's a trivial case. It's not necessary. With me so far? For case 3. Suppose the estimate of p hat is 0.8. Would you say that the claim is true?
I think it must be true because H1 is saying that it's not 0.3, so wouldn't anything not 0.3 be true?
Oh, we talked about the claim. So you're saying you found significance toward the claim? Or against the claim?
It's against.
Against the claim. So you are finding more significance toward the alternative.
Oh, I think I
Right.
moved it around.
Yeah, if p hat is 0.8, 0.8 clearly is not equal to 0.3.
Okay.
So the next question is, well, how far away from 0.3 am I? Is this significantly different from this 0.3? Does that make sense? Okay. Now, going back to case 1. Point 4. That is the null value that I'm starting with for P. So that is my reference, 0.4. Now, in which direction should the data move for me to find evidence toward the alternative? Do you want me to repeat that question?
To the right.
To the right. So it has to go in that direction for us to find evidence toward the alternative. Case number 2. In which direction should the data move for us to conclude or find evidence toward the alternative? To the left. But right. In which direction should data go in order to find evidence toward the alternative? Any direction, right? You go that way, or you go that way. Great. Matthew earlier mentioned, he said, well, if it were to be 0.6, I would say P is greater than 0.4. I find it to be significant. Those were his exact words. If it were 0.6, I would find it to be significant. Since it was 0.45, it wasn't. Well, that's what we think. So Matthew thinks 0.6 is good enough for him to agree with the claim. I might say, oh no, Matthew, for me it's 0.75. Yes? Or Talon might say, for me, pick a number. 0.8, right? So now we have sort of a disagreement, right? How far to the right should you go in order to find support toward the alternative? See that question? How far should you go? Same on this side. How far left should you go for you to agree with the claim? That is P less than 0.1. And in the last case, how far should we go on either side for us to conclude that the alternative is more likely? Yes? So, in other words, we need a standard as to how far one should go. You can't just make stuff up based on what you think or is correct. Now, what is the standard that we use? Comes down to any thoughts?
Could it be 0.05 because?
Wonderful, Paige, exactly.
So how much is like considered?
But get it. Another race. Now, before Paige is correct, could it be 0.25? The alpha? Yes, we're going to relate to that. And before I do get into alpha, so then we had the data had to move far to the right by some degree for me to find evidence toward the claim. Moving to the right, and the first case is a right-tailed test. Second case, take a guess. Left-tailed. No, two-tailed. Collectively, the first two cases, obviously, we call them one-sided tests. Good. Now, Page brought up 0.05. Great. So you may say 0.05 is valid. I might turn around and say, no, I think 0.01 is better. Yes? So you want to use an alpha of 0.05. I'm going to say 0.01. Nick, do you want to pick?
0.001.
0.001, right? So we can change the value of alpha also. In that case, it does become subjective again, correct? Because as a researcher, I might say 0.05 is good enough. Another person might say, no, 0.01 is better. Another might say 0.001 is better. So it is a bit subjective there also, which is why even though confidence intervals are great, there is a tiny amount of subjectivity in them. For instance, when I find a confidence interval, I'm going to go for case number 3, because that is directly related to a confidence interval. So if 0.3 is over here, and you find an interval going back to the interval that I had at the very beginning, 0.27, 0.31. Yes, and 0.3, not exactly in the middle, but it's right here. So that is the interval that we found for P. And what was the amount of confidence that we used? I think it was 95%. Yes?
Yeah.
So %95 confidence, and if the confidence level is 95, what is the value of alpha? 0.05. It was given in the problem, right? The amount of confidence was given in the problem. We used alpha from, or we deduced alpha from the amount of confidence. So alpha is 0.05. What area is on either side? So if it has to fall on this side,
Alpha over 2 and 1
alpha
minus.
over 2, okay. 2.5%. On this side, 2.5%. Yes. This margin is what we call a decision boundary, because this is going to help me either go with the null or the alternative. If, for instance, I say that the value of proportion ends up being 0.49, falls outside that interval, correct? So what amount of probability would you associate with that for it to fall outside of the interval? 95% or less than 2.5%? Less than 2.5% or less than 5%? I'm saying 2.5 because I'm looking at this side only. But strictly speaking, less than 5%. Why? 95% of the time, as we resample and get a new P hat, it's going to fall here. 5% of the time, it's going to fall either on this side or on that side. But sure, I can find a conclusion using that, but if I had let's say 2 samples gave me 2 different estimates, would you consider that this value is just as significant as that value? in going with the alternative, that P is not equal to 0.3. Would you? No, which is more significant?
You're going to get back.
Huh?
0.42.
0.42 is more significant. Yes, more significant towards P not equal to 0.3. All of this happens because I told you what the interval is. Our objective in hypothesis test is not to get an interval, but come to a conclusion as to whether we're going to agree with the alternative or with the null. Where are we going to find evidence, and is it significant or not? So one way to assess that is by fixing alpha, but the better way is to look at values and say which is more significant. And that job is done using the p-value. Good. I will explain what the p-value is soon. We want to know something called type 1 error. Error means a mistake. Anytime you make a decision, you can either get it right or you can go wrong. You make an error, or just don't care. So, alpha in terms of confidence intervals, I call it a significance level. Still is a significance level here, but it has a very specific name. When it comes to hypothesis testing, we call it a type 1 error. What does it mean? Let's say there is this truth. Do we know everything about the population when it comes to statistics? What is the goal behind collecting data, doing all the things that we did? It's to understand what?
Population.
Understand the population, right? So by all means, I don't have a clue about what the truth is. So in terms of the truth, it could simply mean one of two things. You either do not reject the null, or you reject the null. What's the two conclusions? Either I don't reject the null, stick with what I have, reject the null and go with the claim. The test, which is based on data, is going to give me a conclusion. The test might say, do not reject null. Or it might say, reject null. If the truth, hypothetically speaking, there is this unknown truth, which is do not reject null, and you perform this test, you collect data, you perform the test ends up saying don't reject null. Did the test make a mistake? No, the test did not make a mistake. The truth is, you have to reject the null. That's what the universe has for us. But here I collect data and my test concludes, do not reject null. Did I make an error? The universal truth is reject null, which I do not know, but my data is telling me, do not reject null. Did the test make a mistake? Yes. That mistake is what we call type 1 error. The vow that the universe has for us is not to reject null. I don't know what the plan is, but I collect data, I perform a test, and my test ends up saying reject the null. Did the test make a mistake? Why no time?
Because the universal truth is to reject it, right?
Not reject.
Not reject it, and the test results were not to reject, right?
Reject.
Oh, then yes, it was.
Yes. So this error is type 2. Error. The last case, the universe's plan is not to reject null. You collect data, but not knowing that plan, your test concludes reject null. Did the test make a mistake? No. We live in the age of COVID, and you must have heard the word false positive. Yes, false negative. It's been around for a long time. This is nothing but the same idea that's behind false positives and false negatives. Let's say do not reject null means no effect, correct? Hypothetically, I will just say no disease, correct? So in other words, you're negative for the disease. It could be anything. You can for the disease, but all I mean is there is no effect. Yes. In a similar manner, if you say disease, I simply mean to say that there is a true effect. I'm relating this concept to what we are familiar with in terms of tests. And that would simply mean positive. Yes? I could do the same thing here, negative, positive. So you feel sick. Do you know that you absolutely have COVID? No, or any disease for that matter. You don't, you're just sick. But in reality, let's say you don't have a disease, you are negative. You go and take the test also says that you are negative. Did the test make a mistake? No. You have no, you actually have a disease, but the test ends up saying that you are negative. I think this is type 2, that's type 1. Backwards. So backwards, type 2, type 1. So the truth is you have the disease, but the test concludes that you don't. Is it a false negative or is it false positive?
False negative.
It's false negative. The truth is you don't have the disease or effect. You conduct a test and the test ends up saying you're positive. The test made a mistake. So is this a false positive or false negative? False positive. So the other cases here, true, negative. You have nothing and test says nothing. You are positive, the test says positive, so true positive. So by all means, type 2 error is false negative rate, type 1 error is false positive rate. And in practice, it is easier to control for this value rather than type 2 error. We want to minimize false positives. I won't get into the theoretical part of things, but this is the value alpha. So you come up with a test that you say has a 5% false positive rate, but then you collect the data and that rate goes below 5%, all the way down to say 0.1%. So should you feel more comfortable about the conclusion or less comfortable about the conclusion? So your false positive rate that you set at the beginning is 5%. And you're about to conclude positivity, and you end up getting this error value less than 0.1%. So should you be more comfortable about concluding positive or less comfortable? Or you should be more comfortable. And that is the idea behind the test. So I want you to thoroughly understand this before next time.